Okay, hello everyone. So in the last class, we learned, the sp3 hybrid orbitals for carbon. And by this hybriding, allow the carbon to form 4 covalent bonds with hydrogen. So for this hybrid orbital sp3, so one contribution is from 1 s orbital and 3 p orbital. Yeah, so this is why I call it sp3. So I will show you a video.
The valence orbitals of carbon are the 2s orbital and the 3 2p orbitals. When these atoms form methane, their orbitals are thought to hybridize to form 4 equivalent orbitals. Because each hybrid orbital for the carbon atom is composed of 1 part s orbital and 3 parts p orbital, they are called sp3 orbitals. The energies of the hybrid orbitals are the average of the original atomic orbitals.
Okay. So we can use this diagram to show this hybridization process, for example, like the video shows. And so the 2s, this is ground state, and up to this one hybridized, so it forms these 4 equivalent sp3 orbitals. So this each one can pair with 1 hydrogen, yeah, to form the 4 bonds. I think we learned this one before, just a review here. So you know the P has 3 p orbitals like px, py, pz, right? D have 5 orbitals, but S only have 1 sphere shaped orbital. So this is why when they form the hybridization orbitals, we take 1 s orbital, and then we have to take a p orbital. So there not exist this type of the hybridization, just let you know. So yes, we are created as p hybrid orbitals to agree with the shape of the electron geometry. To get the shape first with a Vesper, then we can determine the hybridization. What type of the hybridization based on the shape. So okay, this is a procedure how to determine what type of the hybridization orbitals we have. First, we will draw a Lewis structure as we learned, and then we use a Vesper theory. You know, we did a lot of practice to predict the electron geometry. For example, like the linear, like trigonal planar, like tetrahedral, we should know that by using this Vesper theory. And then we deduce the hybridization type from the number of the electron on the center atom. So this is a very good table, very useful table. Summarized, for example, after you use a Vesper theory, yeah, and so if you have 2 electron units on the center atoms, you have linear, that will be corresponding to the sp orbital. Because you see S is 1, P is 1, you have 2 orbitals. Yeah, so you have 2 orbitals here. That is exactly match here, yeah, 2 units. And of course, these 2 orbitals, hybridized orbital, come from this 2 part, yeah. Similarly, if you have trigonal planar shape and you have 3 electron units on the center atoms, so the hybridization will be sp2. So s2p2 means you have 3 orbitals here. Yeah, altogether S here we have 1, we skip it, and here you have 2. So altogether you have 3 orbitals actually. 3 sp orbital, p2 orbital. They formed by these 3 atomic orbitals. Yeah. So if we have 4 electron units, so the electron geometry, as we learned, will be tetrahedral. And in that case, tetra means 4, right? You have 4 units. That means you need a 4 hybridized orbital. The 4 hybridized orbital can be formed by this sp3. You know, I showed you at the beginning of this class, like the methane CH4. Yeah, carbon and hydrogen 4. That one, there are 4 hybridized orbitals there. It's named sp3. So some tip to memorize that is you have 1s and 3p, altogether 4, right? Yeah. For here, if you have 5 electron units on the central atom, if it's 5, that means you need 5 hybridized orbital. That 5 hybridized orbital can be formed by 1s. As I said, you only have 1s orbital, then you have to use a p orbital. Maximum you have 3 p orbital like px, py, and pz. You have 4 now, but you still need 1 more. So that 1 more comes from d orbital. You take 1 d orbital. So this is what this orbital formed. This sp3d hybridized orbital comes from this 5 part. Similarly, if you have 6 electron units on the center atoms, so the geometry will be, electron geometry will be octahedral, and the central atom's hybridization will be sp3d2, because you need 6. Is 1 plus 3, 4, you need 2 from the d orbital. So this is central atom hybridization. Okay, we talk about lots of the rules and doctrines. Let's see how it works. For example, if people ask you to determine what is hybridization of the central atoms boring here. The first, like I said, you will draw a Lewis structure, and so the Lewis structure will be like this if you draw it properly. And then you check how many electron units on the center atom. You have 3. 1, 2, 3. 3 electron units is it's a trigonal planar electron geometry. And since you have 3 electron units, so you need 3 hybridized orbital. So this is a way. You have 1 and plus 2 this way. sp2 have 3 orbitals like this, okay? This is sp2 hybridization. You see there are 3 orbitals here. 1, 2, 3. This, each one is called 1 sp2 hybridized orbital. Yeah. So then each one form a bond with fluorine atoms, you see. Yeah. So this is an example how to determine the hybridization. So from here, we will introduce a few, introduce the different bonds. The first covalent bonds is named sigma bonds. Sigma bond, in simple word, is end-to-end overlap of the 2 orbitals. So it's the most effective overlap.
A methane molecule forms when 4 hydrogen atoms form sigma bonds to the sp3 hybrid orbitals of the carbon atom.
You see, this shows the end-to-end. Okay, this is a sp3 hybridized orbital, and this is s orbital. So you see they form like end-to-end, or we can say head-to-head. Yeah, head-to-head. This is this way you have the most effective overlap. Here the overlap is maximum. So for this is strongest bond. It's a sigma bond. So this is example how the sigma bond is formed. For example, like the ethene molecules. For sigma bond, and each carbon, like we said, is sp3 hybridized. sp3 means you have 4 hybridized orbitals. 1 plus 3, 4. This is 1, 2, 3, 4. 4 sp3 orbital, and each of these hybridized orbitals form a sigma bond with a hydrogen, like here. And also, one hybridized orbital also forms a sigma bond with a hybridized orbital of another carbon. Yeah. So one thing I want to mention is for sigma bond, the rotation is possible because here, even you rotate this one, you rotate that way, this still form this bond. The bond is not broken. It's rotatable, actually rotatable, yeah. So single bond are sigma bonds. Yeah, this is also single bond. Yeah, all single bond are sigma bond. It's a simple way to memorize it. Yeah, you see, you can rotate it away because this, is highly symmetrical. It's a lobe, so you can rotate it. Yeah, but for some bond, you cannot, like pi bond. We will talk about that later. Okay, we learned a single bond, double bond, triple bond before. So for double bond, for example, ethylene, this molecule is named ethylene. So each carbon has 3 electron units surrounded. Like I said, this single bond is 1 unit, this single bond 1 unit, this double bond, we regard that one as 1 unit altogether. 3 units, so according to the Weisbach theory, the geometry is a trigonal planar, and according to the table I showed you today, it's sp2 hybridization. Again, we could use this diagram. So so this is ground state, electron configuration, if your field build up properly, and then the excited state. So that electron excited to here. So you have this kind of the configuration. And so this 2s orbital hybridized with 2p orbital formed 3 sp2, 3. S here is 1, we skip it, we don't write 1 here. But p is 2, so 1 plus 2 is 3. So we got 3 sp2 orbitals here, hybridized. But another orbital is not hybridized, they keep their original form. It's still pz orbital there. We can use this picture, for example. I think it's very beautiful. These 3 are hybridized orbital. You see, this is a non-hybridized original 2pz orbital. It's a vertical 90 degree, right? Yeah. Okay, this again, I showed you how to determine what kind of hybridization. Like I said, if you have, like previous slide, you have electron units 3, that means it's sp2. Yeah, it's a trigonal planar. Trigonal planar, you see here is trigonal. Yeah. Planar geometry. So this, okay, is another diagram I drew to show you, but I think it's the same story, nothing to talk about. And 2s electrons and hybridized with this 2p, they form only 3 hybridized orbital, but another one keep the same energy. But this hybridized orbital have the energy lower than 2p but higher than 2s. This is why it's hybridized. sitting between. So let's continue to take a look at the double bonds. Yeah, how the orbitals form, the bond formed. So as we said, okay, this hybridized orbital can form the sigma bond with the hydrogen, and form hydrogen, sigma bond with this hydrogen, and these two hybridized orbital also can overlap by head to head or end to end overlap with. It's also a sigma bond. So we have 3 sigma bonds here. How about another orbital that is non-hybridized? How about another orbital that is not hybridized? We know it's a 2p Z orbital. So they will form another type of bond. We call it a pi bond, pi bonding. So this bond, you see, this is orbital, this orbital, just like 2 people, standing on the ground. They shoulder to shoulder overlap. So this is called a pi orbital. We give them a name like pi orbital. If you draw this line horizontally and you draw 2 vertical lines here, you see it's like pi. How you write pi? Draw 1 line and draw 1 vertical line like pi. Okay, anyway, these names people given. Pi orbital is a shoulder to shoulder overlap. But the sigma bond is formed by the end to end overlap of the orbital, right? Let's take a look.
The pi bonds arise from the overlap of unhybridized p orbitals, 1 on each carbon. Note that pi bonding electrons are found in a region above and below the sigma bonding region.
Yeah, they're formed by the unhybridized this orbital. Yeah, they are parallel, yeah, vertical. So, okay, this is the overall picture. This is a sigma bond, like we agree. This is from sigma bond and sigma bond, and the last orbital and hybridized orbital, they form the pi bond. Yeah, you also can draw a picture like this. So this is a pi bond formed between that 2p orbitals. Yeah. For pi bond, there are a few things we should know. First is the side-to-side overlap of the p orbital here, and it's less strong than sigma bond because the overlap, you see the distance is quite long, and the overlap is small compared with the sigma bond. And that pi bond is only exists as a second and third bond of the multiple bonds. Yeah, so if you have multiple bonds, first you should have 1 sigma bond, and then the second and the third will be pi bond. Last, so this pi bond restrict the rotation around the bond. You may remember we talked about sigma bond can rotate this way, but for pi bond you cannot. For example, if this is stick, you have 3 sticks here. If you want to rotate this one, you will break this guy. Yeah, you will break it. So this is why this one is not rotated. Because this cannot be rotated for the pi bond, so that means we will have the restricted rotation around the carbon double bonds. Yeah, for example, this one, you cannot rotate it. Yeah, so it's fixed. The angle and the geometry is fixed. In this case, it will, because the dipole moment here, yeah, dipole, and the overall dipole moment will go up. So this is a polar molecules, if you recall what we learned in the last class. Polar. And this is nonpolar because this one canceled out. The dipole goes that direction, this dipole goes that direction. It's opposite direction. So they can cancel out to each other. So this is nonpolar. So this restricted rotation can make this molecule polar. If we have one single sigma bond without a pi bond, for example, you have one chlorine, two hydrogen here, then they can rotate and but here you cannot. So okay, here is a summary. Single bond is always a pi bond, and for multiple bond, the double and the triple bond are pi bond. The single bond always a sigma bond, and the second and third one will be a pi bond. For example, here, this single bond will be sigma bond, sigma bond, sigma bond, or they're all sigma bond. And this one of the multiple bond will be sigma bond, the first one. The second one will be pi bond. If we have the triple bond, it's the same. Single bond is always sigma bond, and I use different color. So one of them will be sigma bond first, and another multiple bond like double and triple bond will be pi bond. So if you calculate how many bonds altogether in these molecules, so we have 3 sigma bond. You see 1, 2, 3, sigma bond, and we do have 2 pi bond. 1, 2, 3. Yeah. Okay, I think I will not do. I click here and ask you return the center to carbon. Yeah, we are not talking about this one. Only return is to center carbon. How many pi bond? How many sigma bond? The answer is we have 1 sigma bond always, and 1 pi bond. And this is sp2 hybridization. So the last is correct. 1 sigma bond, 1 pi bond. sp2 hybridization, because we talk about that. This is trigonal planar, and you have 3 electron units on this carbon. 3 electron units, so you need 3 hybridized orbital is sp2 is 3. It's 1 plus 2 is 3, according to that table I showed you. Okay, I think briefly I will let you know. Yeah, our teaching contents are always connected to our teaching objective. I posted on the canvas. Yeah, even I don't have time to show this connection all the time, but you should practice and learn by yourself this way. For example, the learning objective I gave to you says you should know how to draw Lewis structures and to determine the geometry, use a Weisbach theory, and we also taught the repulsive force order, yes, and so on. And the dipole moment we learn, and also the hybridization. What type of hybridization is what we are teaching now. So I just repeat, again, to determine the hybridization, for example, you draw Lewis structure, you do Weisbach theory, you determine how many electron units on the center atoms, and then you determine the geometry. Then you will be able to know if you have 3 electron units. So you need 3 hybridized orbitals, will be sp2. Yeah. So for second period for elements, for hybridization in molecules of the second period elements only, yes. If the central atom have 1 double bond, it's sp2 hybridized. If the central atom has 1 triple bond, it's sp hybridized. Because in that case, if we have a triple bond here, you have 2 electron units, 1, and this is 1 unit. 2 units and it's linear. Okay, if we have 2 units, it's linear, it's sp. Yeah. So it's sp type of the hybridization. Okay. For triple bond, okay. Triple bond, you know, you have sp hybridized, only two hybridized orbital. And there are another two are unhybridized. They are, for example, py and pz. So they will form the two set of the pi bond. They form two pi bond. For example, this py and py form one pi bond, and pz also form a pi bond. This is why you got two pi bond, and you have one sigma bond that is formed by by the hybridized orbital. Yeah. So here is not so clear because we skip that part. Yeah, because hybridized orbital here is from the sigma bond. For example, this one is hybridized from this bond. Yeah, and this one forms the one bond with the hydrogen. You see, yeah, this one sigma bond. Yeah, two pi bond between these two carbon. Okay, according to what we learned, for example, how many sigma bond and pi bond are between the two center atoms? Altogether, you have 3 bonds. In other words, how many bonds are pi bond? How many bonds are sigma bond? This is what they're asking. What type of the hybridization we have? As we said, as long as you have the single bond, it's always sigma bond. As long as you have multiple bonds, there only one, always one is sigma bond. All others are pi bond. That means one pi sigma bond and two pi bond here. This is C is correct. One sigma bond, two pi bond, and it's sp hybridization. Okay, I think we finished this part, and okay, yeah, stop. Stop recording.